Okay, welcome back. Here we go. We're going to go on with topic 2. This is the guided note taking. It's a pretty long topic, but at the same time, it is mostly just knowledge based. It's not a lot of difficult concepts to understand. There is a lot of vocabulary, though, however. We're going to start right here at the top. So, after ocean water, the next largest amount of water on Earth is frozen. Large masses of compressed snow and ice exist as ice sheets at the north and south poles and in high mountain tops. These large areas of frozen water cover about 10% of Earth's land area. They lock up about 3/4 of the planet's fresh water supply. In its solid state, let's look more closely at these masses of frozen water, starting with glaciers. What is a glacier? In some areas of the world, it is so cold that snow remains on the ground year-round. When snow doesn't melt, it begins piling up. As it accumulates, the weight of the snow becomes great enough to compress the bottom layers into ice. Eventually, the snow can pile so high that the pressure on the ice on the bottom causes partial melting. Then, the ice and snow begin to slide downhill. This moving mass of ice and snow is called a glacier. Let's go to page 376. How does a glacier form? All glaciers begin as snow. Snowflakes accumulate and gradually become grains, then crystals, and finally ice. Figure 5.8 shows how glacial ice forms. Over time, snow particles change from flakes to grains. Why? Snow crystals have a natural tendency to rearrange themselves into a circular form. The grains are compacted by the weight of more layers of snow. As a glacier melts, water trickles down and refreezes between the crystals. At the time, air is slowly squeezed out of the snow mass. The snow gradually becomes ice. In a similar way, snow on city sidewalks becomes ice under the constant pressure of people's footsteps. For pressure to turn snow into glacial ice in the mountains, at least 30 meters of snow must accumulate in one place. Valley glaciers. A glacier that forms in a mountain range is known as a valley glacier. In high mountains, the average temperature is low enough to prevent snow from melting during the summer. Thus, valley glaciers grow and creep along. Figure 5.9 shows a valley glacier, the Athabasca Glacier, in the Columbia ice field. This glacier covers about 6 square kilometers. Although not the largest one in the ice field, the Athabasca Glacier is the best known. This glacier is the only one accessible by road. The nearby but less accessible Saskatchewan Glacier is almost twice the size of the Athabasca Glacier. We're going to go to page 377 now, and we'll be reading now about continental glaciers. A continental glacier is a huge mass of ice and snow. See figure 5.11. Continental glaciers occur mostly near the north and south poles in Greenland and Antarctica. These glaciers are so thick that they can almost bury mountain ranges on the land they cover. Antarctica is a landmass covered by a continental glacier that is about 932,000 square kilometers. This is about 1 1/3 times the area of Alberta. Glacial features. Ice is neither fluid, like water, nor solid, like stone. The shapes that develop in flowing ice are unique to glaciers. Two such features, shown in figure 5.13, are ice falls and crevasses, where a glacier flows over a steep cliff and breaks up. An ice fall results. A crevasse is a fissure or crack in the ice, as shown in figure 5.14. Let's go to page 379 now. Skip ahead. And we're going to talk about glacial movement. Because of the crushing weight of the layers above it, the ice deep in a glacier is flexible enough to bend, stretch, and flow. This flexibility allows the ice to flow away from areas of accumulation. The ice molds itself to the shape of the rock over which it flows. A glacier is like a river. It flows downhill. It also spreads and thins in wide areas and squeezes and deepens in narrow areas. Most glaciers tend to spread out at the toe where the ice thins. We're going to go on to pack ice and icebergs, and that is on the same page. For most of the year, the surface of the Arctic Ocean is solid with pack ice. Pack ice is a sheet of ice rarely more than 5 meters thick that breaks easily. It is formed from freezing seawater. Large pieces sometimes break off and melt as they move toward warmer waters. Icebergs are large chunks of ice that break loose or calve from continental glaciers as the glaciers flow downslope into the ocean. Each year, about 16,000 icebergs break loose from Greenland's glaciers. Some icebergs are several kilometers long and rise more than 100 meters above the surface of the ocean. As these icebergs float, sun and wind melt the tops. The bottoms of the icebergs submerged in the ocean melt more slowly. Let's go to page 380 to glacial erosion. As they move over land, glaciers act like bulldozers. They push aside and forward any loose materials they encounter. Eroded sediments pile up along a glacier's sides, as shown in figure 517. Glaciers also weather and erode rock. When glacial ice melts, water flows into cracks in rocks. Later, the water refreezes in these cracks, expands, and splits the rock into pieces. These rock pieces are then lifted out by the glacier. This process results in boulders, gravel, and sand being caught by the bottom and sides of the glacier. As the glacier moves forward, rock fragments and sand at its base scrape the soil and bedrock. These rock fragments erode even more material than ice could alone. When bedrock is gouged by dragged rock fragments, marks are left behind. These marks, called striations, are parallel scars or scratches. Striations show in which direction the glacier moved. Moving on to page 381. Evidence of valley glaciers. If you visit the mountains, you can tell whether valley glaciers existed there. Valley glaciers erode bowl-shaped basins, called cirques, in the sides of mountains. Sometimes, 2 or more glaciers erode a mountain summit from several directions. This can form a ridge called an arête, or a sharpened peak called a horn. Figure 517 shows all these landforms. They are evidence of valley glaciers. Valley glaciers flow down mountain slopes and along valleys, eroding as they go. Valleys eroded by glaciers are U-shaped because a glacier plucks and scrapes soil and rocks from the sides as well as from the bottom. See figure 517. In contrast, a valley eroded by a river is V-shaped. We're going to move on to glacial deposition on page 382. When glaciers begin to melt, they no longer have enough energy to carry much sediment. The sediment is deposited on the land. When the glacier slows down, a jumble of boulders, sand, clay, and silt drop from its base. This mixture of different sized sediments is called till. Till is also deposited in front of a glacier when it stops moving forward. Unlike the till that drops from a glacier's base, this second type of deposit does not cover a wide area because it is made of the rocks and soil that the glacier has been pushing along. It looks like a big ridge of material left behind by a bulldozer. Such a ridge is called a moraine. When more snow melts than accumulates, the glacier starts to melt and retreat. Material deposited by the meltwater from a glacier is called outwash. Outwash is shown in figure 5.20. The meltwater carries sediments and deposits them in layers, sometimes in the shape of a fan. Another type of outwash deposit looks like a long, winding ridge. This deposit forms beneath a melting glacier when meltwater forms a river within the ice. This river carries sand and gravel and deposits them within its channel. When the glacier melts, a winding ridge of sand and gravel is left behind. This winding ridge is called an esker, and see figure 5.20. Let's go on to page 385 now. So skipping ahead a few. We're going to talk about ice ages. So over the last several million years, Earth has over the last several million years, Earth has had at least 7 major periods of cooling called ice ages. The most recent ice age began about 120,000 years ago. It ended only about 11,000 years ago. During this period, the climate was very different from what it is today. Glaciers covered as much as 28% of the land. During the last ice age, much of North America was as cold as Greenland is today. Glaciers covered the land from the Arctic to as far south as the Great Lakes. How do we know this? You've seen how glaciers create distinct features in the land. For example, striations, moraines, U-shaped valleys, and erratics are all clues to the presence of glaciers. From evidence such as this, scientists can determine where glaciers have previously existed. So if you look at the figure right here, you can see that right here in white is area that was once covered in ice. So it goes even south of the Great Lakes. Let's go on now to page 386, and we're going to talk about ice ages and climatic changes. A small change in average temperature is enough to start a chain of events that produces an ice age. Why might the temperature of Earth's atmosphere change in the first place? Here are some hypotheses scientists have suggested to explain why ice ages happen. So there are 5 points, possible reasons why ice ages occurred. The first point, there may be occasional reductions in the thermal energy given off by the sun. An increase in volcanic activity may add large volumes of dust to the atmosphere. This might reduce the amount of the sun's energy reaching the Earth. 3. Periods of mountain formations would increase the area of high mountain ranges on Earth. The extra snow remaining on these cold peaks through the summer reflects sunlight and may reduce temperature. 4. The movement of Earth's tectonic plates alters the shape of the oceans. This change affects the flow of ocean currents. With less mixing between hot and cold waters, some regions might become cold enough to start an ice age. And the last, number 5, changes in the tilt of the Earth's axis or in its orbit around the sun may produce colder climates. Scientists are still gathering data to test these hypotheses. Let's go now to page 387. We are almost done. Climatic changes today. We're going to go down here to the next paragraph. As you learned in previous science studies, the greenhouse effect is natural warming caused by gases in our atmosphere, trapping heat. Carbon dioxide is the main greenhouse gas. It is important to realize that the greenhouse effect is not bad in itself. Without the greenhouse effect, life as we know it would not be possible on Earth. Like Mars, Earth would be too cold to support life. Global warming means that global temperatures are rising. Many scientists hypothesize that one reason for global warming is the increase of greenhouse gases in our atmosphere. An increase in greenhouse gases increases the greenhouse effect. In the last 100 years, the mean surface temperature on Earth has increased 0.5 degrees Celsius, or 0.5 degrees Celsius. This increase may very well be due to global warming. If Earth's mean surface temperature continues to rise, ice caps will melt. Low-lying areas might experience increased flooding. Already, some ice caps are beginning to break apart, and sea level is rising in certain areas. Some people believe that these events are related to Earth's increased temperature.